My name is Gottlob Gienger. I'm working for European Space Agency Operations Center in Darmstadt, and subject of my talk was visualizing Earth gravity potentials and perturbed Kepler orbits. Earth gravity potential models and perturbed Kepler orbits sounds a bit exotic. Yeah, this turned out to be was a result of a teaching project here at ESA GOCE. So the presentation starts out with a number of classic subjects, namely very traditional with Newton's law of universal gravitation, then gravitational potential, Poisson's and Laplace's equations, and then the gravity potential or field model of the Earth. Then we turn to the traditional Kepler orbits, which are known since 15th century. Then we look in detail how to solve the Laplace equation in spherical coordinates, look at perturbations of potentials in spherical coordinates on the unit sphere and then in the whole 3D space, and how these perturbations of the potentials perturb the Kepler orbits. And finally, within the presentation, I want to go to the result of some recent space missions. First, how to exactly, precisely measure the gravity field of the Earth, and then present some results from recent space missions, namely JAMP, GRACE, and the ESA GOCE mission. Few notations. There are some formulas needed, and bold quantities, they designate vectors or vector fields in three-dimensional space, and the vertical bars denote the Euclidean 2 norm. Regular fonts are scalars, and in terms of units, I use SI units throughout because otherwise we end up in a mess. Okay, first start with a recap on Newton's law of universal gravitation. There is also a built-in Mathematica formula for that. So it says it's proportional to the product of the two masses divided by the square of the distance. And the unknown constant is g, which was not known at Newton's time. Say if you want to do some calculations, you have to introduce the coordinate systems and you have to write it down in vector equations. Then it looks like in this framed formula. And on the bottom, I attempted a nice animation of Newton's law. The main problem with gravitation is that it's incredibly feeble. So if you have two masses at 1 kilogram, 1 meter apart, the force is about 7 to the minus 11 newtons, and therefore I scaled up the forces here in this animation. So by several powers of 10, and for example, you can here just let the masses vary, or you can, for example, change the position of the mass here, and then look what happens. So, okay, this is classics, and the next step is, instead of the force, we usually look at the gravitation field, and the gravitation field vector is obtained from the force vector by dividing with the test mass, which is in this case m2, and then you get this formula. And in celestial mechanics, usually the masses are denoted by capital M and small m for the capital M for the center mass and small m for the satellite mass. And we just use bold R for the distance vector. A historic excursion on the gravitational constant. This has been measured the first time, or the Earth mass has been measured the first time by the physicist Henry Cavendish in 1798, and he designed a whole building basically to house a torsion balance, which had test masses of about, I think, 500 kilos, and so basically, this is a nice drawing, yeah, of the building, yeah, which he erected. And as I said, he wanted to measure the Earth's mass first, but you can derive the gravity constant from his measurements, and you get this value 6.7 to the 10 to the minus 11 meters cubed divided by kilogram by second squared. And the most recent 2010 CODATA value is not a lot more accurate. Yeah, so it contains just basically two more digits. Yeah, and this is the worst known physical constant, yeah, in the universe. And the problem is, for space flight, we need a much more accurate knowledge, but we can't get more accurate knowledge of the gravity constant, but of the product G times M. Yeah. So now short recap on mathematics. Gauss law for gravity just reads the divergence of the gravity field is minus 4 pi times the gravitational constant times the mass density. Then, since the gravity is a conservative force, you can write it as the gradient of a scalar potential, which is usually called phi. So you can write G as minus the gradient of phi. The minus sign is, I use the convention from physics. And then you can combine these two equations into a single equation, namely divergence of the gradient of phi, which is the Laplacian, is 4 pi times G times rho. And if your mass density in every region where this mass density is 0, you get the simple Laplace equation. Divergence of gradient of phi is 0. And you have Mathematica built-in capability for the Laplacian, yeah, so it's just the sum of these derivatives. Okay, so now we can visualize the gravity potential of the Earth as a point mass. So we use the built-in Mathematica data values from the planet data, namely the Earth mass, yeah, which is about 6 times 10 to 24 kilograms. And we use the Earth average radius. In this notebook, I use the average radius, not the equatorial radius here, which is about 6,400 kilometers converted to meters. And then we can build up the potential function of a mass point and of the Earth mass point potential. And here you see then graphics, yeah, of the radial component of the Earth's exterior gravity potential. This is just the radial component. So at the Earth surface, yeah, you get a potential of about minus 6 to the 7 power 7 meters squared per second. And if you draw it as a figure of revolution, yeah, you get this nice representation. So this is the potential. The gravity field is just the gradient or the negative gradient of the potential field. There are 2 or 3 Mathematica functions which are supposed to calculate the gradient of this potential function. And if you evaluate it at the Earth's surface, yeah, you just get the usual figures of about minus 9.8 meters per second square acceleration. And here is again the radial component of the acceleration. Yeah, so the minus sign means it points inward towards the Earth's surface. And here a vector plot, yeah, of the Earth gravity field. So these are all things, yeah, which some of you may have learned, yeah, a long time, either at school or in an elementary physics course. So now let's look at space flight. We need 2 more functions or quantities, namely to calculate the Earth's escape velocity. escape velocity is that velocity imparted on a mass point, which is just sufficient that the kinetic energy is basically the same as the negative potential energy. Yeah, so it's basically solves this equation and gives out a numerical result. And the circular velocity, velocity is calculated from the equilibrium condition between the inward gravity acceleration and the outward centrifugal acceleration, which, as you may know, is centrifugal acceleration is v squared divided by r, and solved for v. Then you get these two functions, and here I've plotted them. You see at the Earth surface, yeah, the escape velocity is about 11,000 meters per second, and the circular velocity is shortly below 8,000 meters per second. So, and now we can show a few examples of Kepler orbits with different initial conditions. If you start, okay, here is our starting point. So I started here at on the Earth surface, yeah, with an outward pointing velocity vector, which is suborbital below the circular velocity, and then you get a ballistic orbit, and that means you don't get into orbit, but you fall back to the Earth at some point. And these orbits were used here during the Cold War for so-called ICBMs, intercontinental ballistic missiles, yeah, which were supposed to fly from the US to the Soviet Union and vice versa. So if you take the initial velocity exactly tangential, yeah, and equal to the circular velocity, yeah, you get exactly a nice circular orbit. And if you choose an initial velocity which is higher than the circular velocity, which I have done in this case, yeah, then you get an elliptic orbit. And finally, if you change, or if you have an initial velocity vector which is exceeding the escape velocity at the corresponding point in your field, then you get a hyperbolic trajectory. Yeah? So basically you start here and fly on an escape path, yeah, around the Earth. So the calculations are done just and dissolve, yeah, within a very short time. Okay, now a bit of hardcore mathematics, namely Laplace equation in spherical coordinates. What we want to do, we first introduce, of course, the spherical coordinates with the Mathematica convention r, theta, and phi. Yeah, and what we want to do is to define the potential over a domain, both interior and exterior to a spherical surface of a given radius. Yeah, for spaceflight applications, we of course are interested in the exterior potential, and it shall satisfy the Laplace equation and some the boundary conditions on the surface. And in order to do that, yeah, you have to the classic approach is the separation of variables. You separate your potential functions into a radial part and an angular part, y of theta and phi, plug that into the Laplacian, expand it, and then do some algebraic manipulation. Then you end up with this nice formula, and you see there are two terms which only depend on r, and there are three terms, yeah, which depend only on theta and phi, and therefore the first group of terms is equal to an arbitrary constant, and since they sum up to zero, the second group of terms is the negative of that arbitrary constant. Yeah? So we get these two equations. You can try to do it in Mathematica, but you will spend about a day here to do that. Yeah? The solution of this part here is easily found. Yeah, it's just a linear combination of two power functions, r to the power n and r to the power -1 minus n. You can verify here, and I've done this here with Mathematica, that these linear combinations solve the radial part, and that means these power functions are the eigenfunctions of this differential operator here in the denominator. Okay, this is the radial part, and now comes the angular part. If we restrict the Laplacian to the surface of the sphere by setting r equal to 1, we get this simplified version of the Laplacian, and it can be shown that the spherical harmonics y nm of theta and phi are the eigenfunctions of this operator with these eigenvalues. And here is just a short demonstration for the first 10 values. Yeah, so this is the eigenvalue calculation, and this is just the table of minus n times n plus 1. They are identical. This is, of course, not a mathematical proof, but just a demonstration. So, and the spherical harmonics, they are awfully complicated formula. So they consist of a factor depending on n and m, then of a polynomial of cosine theta, and multiplied with a complex exponential e to the power I m phi, and p mn are the associated Legendre functions. And the built-in Mathematica function, they are complex. They are not suitable for our applications. Yeah, so we need to decompose it into a real and imaginary part. So this was the hardcore, and now comes the graphical part. Here is, I introduce here a color function, very simple one. Yeah, positive values are colored red, and negative values are colored blue, otherwise white. Yeah, and then I just plot the first few spherical harmonics. Yeah, the first one is just a simple sphere. The second one also looks like a sphere, but it looks very peculiar. And for order 2, they look like this here. So red and blue parts. So this comes here from it's basically an artifact, namely these are two overlaid spheres. One is blue and one is red, and therefore looks like this. So, and here the imaginary part, also here an overlaid sphere, and the corresponding terms of order 2. Yeah? These are also known or similar functions are known from quantum mechanics. Now, there is a very, very nice classification of these spherical harmonics. They are subdivided into zonal, tesseral, and sectoral spherical harmonics. The zonal ones are those for where the index m is 0, and if the index m is between 0 and n, these are called the so-called tesseral spherical harmonics. This comes from the Latin word for tile, tessera. And finally, if m equals n, then we have the sectoral spherical harmonics. And here, I start here with the zonal harmonics function, yeah, of order 5. Yeah, and now I can just let run the simulation for the index, yeah, over various indices, and then you see on the coloring why the term tesseral and zonal has been introduced. And you see, of course, also the limitations of the resolution of the discretization. So, okay. These are just the signs, and now let's look what happens if we perturb on the unit sphere, if it perturb the identity function by such a spherical function. And one small step is we just need to remove the normalization of the Mathematica spherical functions so that they are comparable with the one. Yeah, and then we get in coarse resolution. Yeah, we get these functions on the unit sphere. So they look a bit odd, yeah, but I had to limit basically to to speed a representation, otherwise it may lock up my computer. Okay, and if we go here, increase, say, to the maximum, just march, then you see what it's all about. And I need to go to speed representation. Yeah. This is what, yeah, you get very strange figures, yeah, which are all in this group. Okay. If you're patient, yeah, you can use the high resolution and you see it much better. But as I said, it may lock up my computer. Therefore, I prefer to have my own. Yeah. So now these are where the spherical harmonics, they can be extended to the whole space by the spatial part. And this is done by expressing the complete real solution of the Laplace equation then as a linear combination, yeah, of the spherical harmonics here and here multiplied with the radial solution r hat to the power -1 minus n, where r hat is just the dimensionless ratio between our radius and the function of and the radius of the sphere. Then you can do various algebraic manipulations with that, and you factor out. We want to insert or factor out the potential of a point mass. Yeah, in this case, the Earth minus g times m Earth divided by r. Put that in front, and then we end up with this representation, yeah, of our spherical harmonics, which I have used then for the subsequent calculations. And here now I show you the equipotential surfaces of these disturbed potentials, yeah, with these spherical, solid spherical harmonics. And this is so just starting with order n equals 2 and index m equals 1. And if I let run here the index, yeah, you get also the sine part. And what you see here is that the inner equipotential surfaces, they are have large deviations from spherical shells, whereas the farther you go out, then they more and more approach spherical equipotential surfaces. That means the potential approaches the 1 over r. Yeah. Okay. So. And now the last part. Let's look what these solid spherical harmonics, yeah, do to a Kepler orbit. Yeah. So I started again here with an order n equals 2. Yeah. So that means basically it corresponds to a flattened Earth. Yeah, and calculate a Kepler orbit with a certain initial conditions. And then you can see, yeah, now strange things happening. This is here are the initial conditions. So we started at 500 kilometers altitude, and the Kepler orbit, of course, is close to a circular orbit. It's planar. Yeah. But if you introduce such a perturbations, yeah, from flattening of the Earth, what happens is that you get very, very strong perturbations. The orbit is no longer planar. Yeah, it's not closed. Yeah, it's bent. Yeah, also outside of the plane. This is, of course, all highly exaggerated. Yeah, in nature, such strong perturbations don't occur, but you can't see them. Yeah, if you use the coefficients from actual Earth, you won't see anything. Yeah, yeah. So okay. So I just hesitate to change the setting here because it may lock up my computer. It takes about 20 seconds here to. What's happening here? Okay, now let's look how we can precisely measure the gravity field of the Earth. First of all, we need to understand the definition of the geoid. Yeah, it's the shape of the surface of the oceans would take under the influence of just Earth's gravitation and rotation alone. Yeah? And the geoid means that if you put a plumb line above it, it's just perpendicular to the geoid, and the water level is parallel to the geoid. And then there is also important concept, the reference ellipsoid. It's just a mathematical defined surface that approaches the geoid. So what one can do in practice and has done over the last more than 200 years, you can measure the surface gravity with so-called spring gravimeters. This figure just shows you the principle of that, and they have, in the meantime, now a really astonishing accuracy, 10 to the -8 meters per second squared. And since the spaceflight age, you can use, for example, satellite tracking, and the most precise one is with satellite laser ranging, and the most prominent species of that is the laser geodynamic satellite launched in 1976, which is still in orbit. It's a metal ball of 400 kilos with laser reflectors. And you can use satellite altimetry, and the last picture shows the principles of satellite altimetry. Now let's come to the space missions and results over the past 1.5 decades. The first one in this sector was the CHAMP mission, which stands for Challenging Mini-Satellite Payload. It was a German mini-satellite project which was developed by Geoforschungszentrum in Potsdam, and 10 years mission duration, and did highly precise gravity and magnetic field measurements. Here you see, this is a picture of the satellite, and it shows here, the logo shows all the organization which were involved in that. And here you see one of the scientific results of the CHAMP missions. This is the geoid here as determined by CHAMP, and let's see if that works. So this is, of course, again, highly exaggerated, the geoid figure obtained from that. Okay. Next mission in that sequence was the GRACE space mission. This was also a small space mission of 2 tandem satellites, cooperation project between NASA and the German DLR. Here are some more facts on the mission. The important thing is it consisted of a tandem of satellites, which flew on the same polar orbit. And the important new feature, what they used an RF microwave link, which exactly measured the distance between the satellites as they passed over the gravity anomalies. And this gives enormous precision measurements on the gravity perturbations. And here are some results from the GRACE space mission, also the gravity anomalies, and here gravity anomalies over the oceans deduced from this mission. Okay, and the last thing in that sequence is ESA, the GOCE space mission. GOCE stands for Gravity Field and Steady State Oceans Circulation Explorer. It was launched in 2009. The mission has already ended because it was at a very low orbit at 260 kilometers, and there it had always experienced atmospheric drag, and therefore it needed an ion engine basically to to constantly push it, yeah, and as soon as the fuel is exhausted, the thing re-entered, yeah, and burned up in the atmosphere. And here you see the two of the gravity field models from the Gauce mission, one at the beginning and one at the end. Yeah, and that concludes the presentation, and